Okay, so this is Physics Unit 3. We are on page 8 towards the bottom. So we're on number 13. Anne, with a mass of 50 kilograms, and John, with a mass of 80 kilograms, are standing on frictionless skateboards. So, frictionless. John pushes on Anne with a force of 300 newtons. Find Anne's acceleration. So let's draw a picture first. So it doesn't need to be anything complicated. Here's a skateboard, and here's a skateboard. So this will represent John, this will represent Anne, and this will represent force that John exerts on Anne. We're looking for acceleration. We know masses, we know force. That's enough information that we could use Newton's second law, which says acceleration is equal to the net force divided by the mass. So we're going to say the acceleration of Anne is equal to the net force on Anne divided by the mass of Anne. So the net force, we have to think about all of the forces that are going on here. So there's a force of 300 newtons that is trying to accelerate Anne. In the opposite direction, we would include friction. However, this tells us that there is no friction. So the net force is the force of the push minus friction. 300 newtons minus 0 newtons. And then Anne's mass, which is 50 kilograms. So we have 300 newtons divided by 50 kilograms, and we find that Anne accelerates at 6 meters per second squared. So in all of this, describe what happens to John. The force exerted on John is 300 newtons in the opposite direction. So if John exerts a force on Anne, Anne is going to exert a force back on John. It will be an equal and opposite force according to Newton's third law. So the force on John is 300 newtons in the opposite direction. What about John's acceleration? Again, the net force is, here's the force exerted, minus the friction, which we're frictionless here, so we have a friction of 0 newtons, divided by John's mass, which is 80 kilograms. And so John's acceleration is 3.75 meters per second squared. And of course, this would be in the opposite direction from Anne. Would your answers change if Anne had done the pushing? So look up here at our picture. Would this scenario have changed at all if Anne was the one exerting 300 newtons of force on John? Well, Anne would have still had a force of 300 newtons acting back on her. John still would have had a force of 300 newtons acting on him. Their masses would have remained the same. So would these answers change if Anne had done the pushing instead of John? The answer here is no. And the reasoning behind it is action, reaction. So this is at the top of page 9. two people on a frictionless ice push against each other. A person with mass 45 kilograms accelerates west at 2 meters per second squared. Find the acceleration of the person with mass 100 kilograms. So again, let's draw a picture. It's always going to be helpful for us to draw a picture. So here's my frictionless ice. So some physics pictures here. Here is a person that is mass 100 kilograms. Here is a person that is mass 45 kilograms. So they were probably touching, and then they pushed against each other, and person with mass 45 accelerates at 2 meters per second squared towards the west. Remember, our compass directions: north, east, south, and west. So there's west, just like we're looking at a map. What is the acceleration of this person, the mass 100 kilograms? So we have to figure out what is the net force acting on my 45 kilogram individual. So remember, net force is mass times acceleration. So the mass is 45 kilograms, and we know the acceleration. It is 2 meters per second squared. So the force that was exerted on this 45 kilogram person was 90 newtons. Then we can figure out the acceleration of my 100 kilogram person. So the net force is going to be the same for each of them. So the net force of the 100 kilogram person on the 45 is 90. The net force of the 45 kilogram on the 100 kilogram person is 90. They are equal. The accelerations will be in opposite directions. And mass is 100 kilograms, and so we see this is 0.9 meters per second squared. There is an alternate method. So I'll write the alternate method here. And this is basically where we say the force of the 45 pound person equals the force on the 100, newtons person. And so we fill in our numbers. So we know mass times acceleration. So mass of 45 kilograms, acceleration was 2 meters per second squared. And the force of the 100 pound person, we don't know everything. We're looking for acceleration, but we know mass, and we can solve for the acceleration here. So this is F, this is MA, here's F, here's MA. And so we can divide both sides by 100. That's not meters per second squared, that was 100 kilograms. We're looking for acceleration. So kilograms will cancel out, and we're going to have meters per second squared. 90 divided by 100, and we get 0.9 meters per second squared. Same acceleration. Remember, these are equal and opposite. Forces are equal and opposite. So as Newton sat under an apple tree, an apple of mass 0.25 kilograms, fell to the earth. The apple accelerated to the earth at a rate of 10 meters per second squared. Find the following pieces of information. So A, find the force exerted on the apple by the earth. So let's draw, here's the earth, here's the apple, and here's the earth. So the force that the apple is going to exert on the earth is mass times acceleration. So let's write this down. Here's mass, here's acceleration. That means it has a weight of 2.5 newtons. So its weight is 2.5 newtons. When it hits the earth, equal and opposite. The earth is going to exert an equal and opposite force of 2.5 newtons. The force exerted on the earth by the apple, 2.5 newtons. Remember, we're talking about action-reaction pairs. C, the acceleration of the earth due to the force exerted on it by the apple. And the mass of the earth, we've used this value before, 6 times 10 to the 24th kilograms. So we have an acceleration, we have a mass that's good for using Newton's second law, the net force divided by the mass. And specifically, this is mass of the earth. Acceleration of the earth. So the acceleration of the earth equals the net force divided by the mass of the earth. Net force is 2.5 newtons. Mass of the earth, 6 times 10 to the 24th kilograms. And we find an acceleration of 4.17 times 10 to the negative 25th meters per second squared. When an apple falls to the earth, does the earth move? Well, according to this, it is accelerated. Does that mean we can detect it? Can we notice an acceleration of this amount? Most likely not. A tractor is hooked to a log with a strong chain. The tractor pulls on the log, but according to Newton's law of action-reaction, the log pulls back on the tractor with an equal force. So how does the tractor move the log? So let's draw a little sketch of what's going on first. So let's see, here's my tractor. And let's see, here is my chain. Here's the log we're talking about. And here's the ground. Imagine that these are actually touching. There you go. So the log will move if there's a net force on the log. So draw all of the forces on the tractor and the log. So let's see what all we've got here. Let me actually move this out of the way. Draw the tractor higher. So first off, we have force of the tractor on the ground. So there's the force of the tractor pushing on the ground. In order for the tractor to move forward, the ground has to exert an equal and opposite force on the tractor. Then we also have the log back here. So here in this direction, we have the force of the tractor pulling the log. And back in the other direction, we have the force of the log pulling on the tractor. There's one more force that we should probably label, and that's here, and that would be the force of friction. So the log will move if there is a net force on the log. So as long as the force of the tractor on the earth exceeds the frictional force of the earth on the log, then there will be a net force on the log, and it will accelerate. Isn't that what your common sense says anyway? The action-reaction pair forces, remember, they act on different objects. So we have the tractor acting on the ground acting on the tractor, equal and opposite. We have the force of the tractor acting on the log, force of the log on the tractor, they're equal and opposite. As long as there is a net force acting on the log, then it's going to accelerate. And for just a second, let's ignore all of this. Don't actually scribble this out. But if you just look at the log by itself, look at this. We have a force pulling it to the left, and we have a small frictional force holding it back to the right.